Okay, welcome back to the student papers part of the second session of the TUAC. Our first paper is entitled Comparison of Different Classifiers for Age Recognition System-Based Speech Signals. The writers are Armağan Fidan, Rabia Özgebircan. They are from Boğaziçi University. Armağan and Rabia, you can start.
Thank you. Let me share my screen and open PowerPoint. Yeah. Our project is comparison of the different classifiers for age recognition systems on speech signals. And why do we need this project? We think about the security reasons, first of all. And the problem about the security reasons is basically about the user identifications. And it is the same problem in the forensic science and commercial advertisement. In the commercial advertisement side, some people think that if we can scope onto the age labels, we can increase the overall sales. At the end, which database we used in the speech recognition system, age recognition system, is basically the Mozilla Common Voice. In the literature, this is most commonly used, one of the most commonly used database, and the other one is the NIST database, but unfortunately, NIST database is required and access requests to the NIST, and that's why we use Mozilla Common Voice. And the structure of the system, we take the speech signals on the database and we clean the data because there are so many labels on the data, which accent they are speaking, which text they are reading, and we just only need the gender and the age labels, and we clean the data according to that, and then we create an unvoiced extraction algorithm. After unvoiced parts, elimination of the unvoiced parts, we extract some features and we train the model according to the features. In the unvoiced extraction part, what we did is we take the signals frame by frame and we applied zero crossing rate and root mean square energy. And if zero crossing rate is tend to be higher, it means that this is the signal, the frame is basically noise part of the signal, and if root mean square energy is lower, it means the same thing. We are doing the cross check on the frames, and if the ZGR is small and the RMS is high, it means that this is the voice part of the signal. If the threshold doesn't hold with our values, that means that we need to subdivide the frames and redirect to the algorithm again. After the unvoiced extraction, nearly 40% of the signals is deleted, eliminated, and pure signals are obtained from the unvoiced detection algorithm. And then we apply some extraction, future extraction methods, and one of them is the most contributing one is the mel-frequency acceptable coefficients. We extract 13 MFCC, and we also took the PLP, spectral growth, and other features as well. And at the end of the day, we had 318 feature vector, and unfortunately, when we fed into our model, it's just overfitting. And it is to have a higher dimensional feature set is not an obligation to have a better model. And that's why we use the principal component analysis to reduce the dimensionality from 318 to 85. And then after the future dimensional reduction, we use different machine learning models like multi-layer perceptron, support vector machine, long short-time memory, RNN networks. And the best result came from the MLP multi-layer perceptron. It's maybe because of the fact that this feature is completely becoming with the numbers, and multi-layer perceptron is very good at the numeric values. Convolutional neural network is giving a bad result because of the because of the reshaping and eliminating some of the features and trying to take the features and isn't the picture networks. And support vector machine, the KNN, is the other algorithms that we used. And the second of the best result came with the KNN network. And we should, as we seen in the figure, the best result is on the multi-layer perceptron with near to the 19 accuracy. This is the best result, one of the best result on the literature. And if we want to make, if there is need to have a faster model, the KN is the second option, and it is run faster, a lot faster than multi-layer perceptron because of the complexity of the networks. And random forest, we couldn't find the cross validation because of our systems, computer systems, and we take from another literature, and the literature found that near to the 80 accuracy on the random forest, and the others one as we shown in the figure. And the future of the age estimation system is application will be increasing with over time because of the IoT and the AI field, and the security concerns will be becoming bigger and bigger, especially in the bank systems. And because of this coronavirus pandemic, the need of the user identification from far away is becoming a very crucial topic, and the future age estimation system could be one of them. And in the future work, what we are trying to do is that we are trying to take a more dimensional feature vector, and we try to do future importance from them. And with future reduction, we are going to focus on the MLP in the future work. And thank you for listening.
Let me open my thing. Okay. Thank you very much. So, like, what do you think about like age estimation with all the masks and so on? Will the computers can do that or not?
Can you repeat the question?
During the COVID, everyone has masks and all those things, and I believe that age estimations will be a really, really hard problem. What do you think?
It depends on actually it depends on the data set we can take. I mean, if we increase the data set with respect to the variety of different users, that means that we can train our model with better accuracy in different areas. Now it is about to complete about the data set. Our data set does not include the that type of scenario. Our data set consists of the users who's using their own computer and microphone. And if we increase the data set with that scenario, yeah, I think that we can use this user identifications on age estimation with SPECH.
Thank you very much. I'm checking the chat. There's no more questions. I would like to thank you for this nice presentation and go to the second presentation of the day. Design of 4-bit and 8-bit pseudonoid sequence generators with all zero condition protection circuits. It's from Alper Kurt. Alper is from Özyeğin University. So we are waiting for Alper to join. Okay, Alper is here. Alper, can you share your screen, please?
Let me share my screen. First. Yes, can you see my screen?
Yes, we can. We can go to. Yes, you can start. Thank you.
Okay, so today I'm going to present my paper, which is a title of Design of 4-bit and 8-bit pseudonoid sequence generators with all zero condition protection circuit. Actually, let me start with a simple question. And what is pseudonoids, or in other words, PN sequences? Yes, okay. And pseudonoid sequences are binary sequences, and this sequence is a periodic signal which can be locally generated in both transmitter and receiver side. So therefore, they can be utilized as wideband with signal for radar ranging and remote synchronization with high accuracy. And also PN sequence is a deterministic signal which has a finite length. This length might vary. However, for a specific condition, it is a maximum length. And this maximum length is 2 to the power of m-1, but I will talk about what is the m in the next slides. PN sequences can simply be generated by digital circuits using a linear feedback shift registers, in other words, LFSR. And these LFSR is formed with D-type flip-flops and exclusive OR gate, as you can see here. Actually, the feedback mechanism of this LFSR is determined by the feedback polynomial. And this is the feedback polynomial for 4-bit PN sequence generator. And in other words, the m is equal to 4. And when we examine this feedback polynomial, we can see that the output, the power of these X terms are called tabs. and these steps determine which output of the D-type flip-flops will be applied to the XOR gate, as you can see here. And the 1 stands for the feedback mechanism. Actually, the output of the XOR gate will be applied to the first input of the first D-type flip-flops. So this is the all states of LFSR. Actually, you can see that Q1, Q2, Q3, and Q4, these are the output of the D-type flip-flops. And the 0th state of this LFSR is called initial seed. Actually, it means that these are the first bit values of the D-type flip-flops. And actually, this value is not really important for PN sequence generator, but if it's in a all zero condition, in other words, if all the bits are zeros, then the system will be locked and PN sequence will never be generated. So therefore, we need to find a solution, and I will propose a circuit in the next slides to handle this problem, the all zero condition protection circuit. But for now, let's assume that there is an initial seed is given like that. And when this is the initial seed, this is the 4-bit PN sequence. Actually, this is since this is the 4-bit PN sequence, the length of this PN sequence will be 15 because of 2 to the power of 4 minus 1. And you can see that after 15 bits, the 16th bit will be exactly the same with the first bit. And the 7th bit will be exactly the same with the second bit because of the periodicity. Also, these are the polynomials for different value of the m's, and these are the maximum length with respect to degree of m. Here again, degree of m means that the number of D-type flip-flops that were used in this circuit, or simply it's the bit values, 4-bit, 8-bit, 16-bit, or etc. And also, it's obvious that the maximum length extremely increases when the degree of m increases. Before I started to mention about the implementation, actually, I want to clarify that this PN sequence generator can be implemented with FPGA, with VHDL or Verilog. However, I want to design a system, I want to propose a system for a low-cost alternative to this FPGA implementation. And also, I want to design a system which can be plug and use, which can be used for different systems for different frequencies. So I started to my design with clock generator circuit. Actually, I use a timer IC, 555 timer IC, to generate a clock which has a 100 kHz frequency and 50% duty cycle. However, this is not a crucial design because the clock can be fed with external resources from any resources, let's say signal generator or anything else, maybe microcontroller. So that's why this is not a crucial part of my project, but I want to design my own clock generator circuit. I also designed a 4-bit PN sequence generator. You can see that there are 4 individual D-type flip-flops here. But instead of using 4 individual D-type flip-flops, I use an integrated circuit, which has 4 integrated D-type flip-flops. The idea is the same. The feedback path is the same. I use an XOR gate, and I add a button in order to set the initial seed. Actually, if there is no button there, the PN sequence generator will never be working. The PN sequence will never be generated because it will be in all zero condition. All 4 bits will be 0. So when I immediately press the button, the PN sequence will be generated. However, this is not a good solution. This is a temporary solution. As I mentioned it, when I propose a all zero condition circuit, this circuit will be replaced with this button. This is the output waveform of the 4-bit PN sequence generator. You can see that the output waveform is changing with the rising edges of the clock. And this is the binary sequences of the PN sequence generator. And also you can again see that the 16-bit and the 17-bit are exactly the same with the first and the second bit. I also design 8-bit version of this PN sequence generator. I again use a 8-bit integrated IC, and I also use an XOR gate, and I also added a button for the same reason, to set the initial seed. But again, this is a temporary solution. I will replace with this button with a all zero condition protection circuit. Actually, on the simulation, I successfully generated the 8-bit PN sequence. However, since it's too long, I did not plot the output waveform of that. And so what is that all zero condition protection circuit? Actually, this circuit ensures that the all zero condition will never occur in the circuit. The fundamental idea of this circuit is counting the rising edges of the clock. There is a 4-bit binary counter, and it counts the rising edges of the clock. And if the number of counted rising edges of clock is less than 6, then the output of this NAND gate will become 0. So the become 1, sorry. And this one switch on the relay, and this relay will be pull up this node to the VDD, or in other words, to the 1. So by doing that, this ensures that one of the nodes, I will connect this node to any part of the LFSR, one of the nodes will become 1 instead of 0. So it ensures that the all zero condition never occurs. And at the same time, since this node is 1, I applied the clock with 1 to the AND gate and output of the AND gate to the binary counter. So since here is 1, the output will become clock, and the clock is applied to the binary counter. However, when the number of counted clocks is exactly 6, these four output will become 0, 1, 1, 0. And due to inversion, it will become 1, 1, 1, and the output of the NAND gate becomes 0. So when this node will become 0, the relay will be switched off, and this node will be open, and from now on, the PN sequence can freely be generated. And at the same time, since this node is 0, there will be no clock is applied to this integrated circuit anymore, and the counting will stop. So this is the basic idea of the circuit, and you can see that these are the all states of the LFSR with protection circuit. You can see that for the first 6 clock, it ensures that this node become a 1. It forced to become a 1, and after the 6 clock, the PN sequence generator will be generated as it should be. There are some advantages of this condition protection circuit. Also, exactly this, there is no need for external impulse work. We don't need to press the button, or we don't need a microcontroller to start the PN sequence generator. And again, it ensures that all zero condition never occur in the circuit. And also, PN sequence generator can be fed with an external clock. This is important because clock and power can be applied at different times. If there is a time delay, actually, if there is a little time delay between the clock and power, I also tried it by myself. The PN sequence generator will never be start, but for this protection circuit, it will ensure that it will start because it will wait for a clock. So I want to apply a clock maybe after 30 minutes that I power the system. So there is no limitation for the timing of the clock and power due to this protection circuit. To conclude, 4-bit and 8-bit PN sequence generators were designed. All zero condition protection circuit was proposed for hardware implementations of PN sequence generator. And also, as I mentioned, the low-cost hardware alternative was given to FPGA implementation. After I wrote this paper, actually, I did some experiments on the lab, and I manufactured some of the design on the lab. But I used different ICs because I decided to use higher frequencies. It was 100 kHz in the paper, but I use 4 megahertz in the lab. So I need a very much smaller rising and falling time for the ICs. So I use different ICs, but the idea is the same. There is a D-type flip-flop IC, there is an XOR gate, and there is a reset button. And I also constructed the protection circuit on the breadboard, and I also manufactured this all zero condition protection circuit. And this is the final version of my project. There is a clock generator part, but as I mentioned, this is not a very crucial part. Actually, in the paper, it was a timer IC, but I used VCO in order to get higher frequencies. But again, this can be applied with a signal generator. So this is a PN sequence generator core, and there is an initial protection circuit with a 5-volt relay. And this is the output waveform of 8-bit PN sequence generator, and it was successfully generated in the lab. So this is the final PCB version of my design. There is a protection circuit, there is a clock IC, and there is a D-type flip-flops IC and XOR gate. And these are the integrated circuits that I use for this design. But again, the clock IC is not necessary. Maybe for a product, I don't want to use a clock IC because I want then every people can apply its own clock. So this is the final version of my project, and thank you for listening to me.
I would like to congratulate you. You didn't stop at the simulations and so on, but you actually did produce it. We are a little bit behind time. I didn't get any questions. So what will be your next project? Do you have anything else in mind?
Yes, hocam. Actually, this is a part of another project. Actually, I want to design a delay lock loop system for a radar synchronization. There will be radar on the ground, and there will be plane, and we want to measure the distance between the radar and plane. And for synchronization, I want to design a delay lock loop, and this is the main part of the delay lock loop system. So that's why first I need to manufacture a PN sequence generator for my project. But since I tried to manufacture it, I want it to be it will be ready for all systems for any frequency. I want them that everybody can use a PN sequence generator if it's needed.
Thank you. Thank you very much again. So we can go to our next speaker. The name of our speaker is Halil Said Cankurtaran from the IEEE Turkey PDAA. And the title of the work is Mean Energy-Based Audio Visualization Method. So Halil, you can share your screen.
Okay. Can you see my screen right now?
Yes, we can. You can start.
Hello everyone, my name is Halil Said Cankurtaran. I will try to present you mean energy-based audio visualization method paper. In the presentation, I will make a brief introduction and explain my motivation, and I will introduce the proposed method and explain my measurement campaign, and I will share a conclusion and results. As you know, with the advancements in electronics and communication technologies, the world shifted into a new world, and there we have seen a paradigm shift. With the development of mobile phones, people have started to use their mobile phones to surf on the web or to watch videos or to share ideas and thoughts. That's why mobile have dominated the desktop in the use of internet. And there are several websites and social media platforms which are visited by billions of people every day. YouTube, TikTok, and Instagram is the most important and most popular ones. The common thing that they have is they offer highly visual content to their users. That's why they are so much popular, because people want to watch video or look at pictures instead of reading text or listening something in the internet. But there are some other category called podcasts, and people share their conversations, and other people listen to have fun, learn, or utilize their waste time. But if you want to share your podcast on the YouTube, you need to visualize your audio recording to not to violate customs of YouTube. That is the main motivation of our study or work. I want to just briefly mention podcasts, history of podcasts originating in the 1980s when the internet had become a real thing, and it's called asynchronous internet radio at the beginning. When Apple introduced iPod and podcast application, it's called podcasts, and it's called now podcasting. In 2018, there are 18.5 million podcast episodes. In April 2021, there are 48 million podcast episodes. And as you see in the numbers, people listening podcasts are increasing day by day. And you can find podcasts in any category and in any topic if you search on the applications like Apple Podcasts. As I mentioned, our main objective is developing an audio visualization method based on the mean energy of the audio recordings. To create an audio visualization, we need some kind of inspiration. We have to create a visual. That's the first milestone. And secondly, we need to create our mean energy calculation software and visualization software. And at the end, we test the audio visualization method and optimize all parameters. I thought that we need some kind of inspiration, and for inspiration, we thought that Kit might be a suitable sample for this project. Kit is the car in Knight Rider series in Turkish, I think, Kara Şimşek. It is one of the most popular series in the world in the 1980s, and it affected lots of children at that time, and it increased the interest on the artificial intelligence and computer science, I think. And on the screen here, when Kit talks, there are some kind of indication rising and downing, and we wanted to use that visualization in our project. But as I mentioned, we have to calculate mean energy of chunks. By chunks, I mean we divide audio recordings into several chunks based on the frames per second requirement. In YouTube, it is said that you have to upload your video on 25 frames per second, but if you use 25 frames per second, you can see the visualization effectively. That's why we first create our visualization on 10 frames per second, and then before uploading to YouTube, we change the frames per second parameter of the video. But in order to have decent visualization, we have to shape distribution of energy. That's why audio recordings, acoustic signal, human speech signal, energy of human speech signal is concentrated around a specific point, and we have to stretch that distribution to create some sort of visualization. That's why we need shape distribution of energies. Then we visualize or calculated energies and save video and upload to YouTube. Basically, our measurement campaign requires only a microphone and a laptop to execute our code. And our code has been published on the GitHub page of TAPILab. You can access and use it. And this is the one of the frames of the our podcast. And I want to share also one of the visual content, like when I talk, it goes up and down. Thank you for listening to me.
Thank you very much for this interesting talk. So are you planning to improve this one, or is it the end product, I would ask?
No, it is the first product actually, because it's very basic. It only considers the energy calculation. It doesn't consider where the actually talk is. For instance, if there is an environmental noise in the recording, it shows that as an activity. That's why we need to implement some sort of voice activity detection. Also, we can improve the visualization. It is just basic rectangles, which is inspired from the kit car, as I said.
I see. Okay. Thank you very much again. We can go to our next speaker, Orhun Arık from Özyeğin University, and the title of his work is N by N Bit Multiplier in M cycles. Orhun, could you share your screen, please? Okay. And you are still muted, so unmute yourself. Thank you very much. Yeah, you can start your presentation.
Thank you. So my name is Orhun Arık, and I have been working for my final term project, and it's actually the same as the TUAC project which I submitted. It is the M by N bit multiplier in M cycles generator. That is kind of missing in the TUAC report, so this is actually a generator research. And my supervisor has been Hasan Fatihullah. Okay. So I'll be doing an introduction and then some methodology and tools and standards. And yeah, as you can see, the slides will progress like this. So why do we need a multiplier? Well, why do we need an M by N multiplier? Well, what I do in this research is that, project is that I actually apply resource sharing to the processes, which will decrease the circuit's area, and it can even increase the decrease the power consumption. So this is this project is specifically based on FPGAs, where we can decrease the area for specific needs, and also the inputs are going to be in the thousands of bits. And these images you see here, they will be relevant. I'll be talking about them in the future slides. So we have FPGAs. What are FPGAs? And these are actually, this is a blank digital circuit which you can, design digital designs, and you can test them out on these. So you don't have to manufacture them, which is why this project is better applied than these, because we can actually increase or modify the multiplier as we like, according to the FPGA's specifications. Okay. And we have LUTs in FPGAs, which is basically a Mux network, and it stands for lookup tables. And we use these for multiplication results and etc. We also have flip-flops, which we can store data in, and then send them out on the next cycle. And we need UART, which is a universal asynchronous communication protocol. So we need this because the input bits are in the thousands of bits. We actually apply a UART connection with the PC instead of using the switches on the FPGAs, which obviously there aren't enough of. And with this project, I used Xilinx ISE, Vivado, and Jupyter Lab and Notebook, where I utilize Verilog and Python so far. So I would like to talk about the wrapper, even though, well, this is a 32-bit by 32-bit multiplier, a simple multiplier with a default star operator. But the important thing here is the wrapper. So we have the UART connection, and we take the inputs and store them in flip-flops. And then once the inputs are completely filled into the flip-flops, then we utilize the multiplier and take the outputs in the same manner. And we can also have these IP core generators, intellectual property generators. So this is actually a benefit of Xilinx ISE. So, and as you can see with the wrapper, it looks exactly the same. It just generates the multiplier, not the wrapper. So we have, moving on to the algorithms, we have the schoolbook algorithm, which we are familiar with from primary school. We shift, in this case, if it is 1, we shift and add the shifted version to the final product. But there are actually better algorithms. So the images on the right show the schoolbook algorithm working. And as you can see, with 32 bits by 32 bits multiplications, it takes 32 cycles. Well, starting from 0, even though it says 31 here. I don't know if you can see that. So this is even more further results, although there is a problem with the final 4 bits. So that is something to look to fix in the future work. And then we actually progress to other designs. So we can have 32 by 16-bit multipliers, and we can compress this 32 cycle operation into 2 cycles. So we take the 32 bits input from the input 0, and then take the 16 bits from the second input 1. We multiply 32 by 16, put that into a register, and then take the other half and shift that and sum them up. And as you can see, it can actually generate results in 2 cycles. So furthering this concept, we can have a different a feedback adder in the system, and we do this by putting a register and summing everything, and then in the first cycle we feed it into the register, and in the second cycle we sum the register and the new product together. And it's important to note that here in this version we use a unit multiplier. A unit multiplier is a partial product generator, a Wallace tree, and an adder. And a unit prime multiplier is just the partial product and the Wallace tree, which I'll be talking about in the future slides. And again, it works with them 2 cycles. So with the unit prime multiplier, we can actually split them into, well, split one of the inputs into 4 sections, so that we can have 4 cycles. And as you can see, the cycles are actually increasing with these with these changes in the algorithms. And we utilize the unit multiplier. So it just does the partial product generation and the Wallace tree compression, but the final adder is here. So we have actually gained some area from this application. And we also have a 4x2 compressor. And again, using a register, we can add everything up together until we get the final product. And again, as you can see, it works with 4 cycles. Well, the blue ones actually indicate the cycle, well, the final products. So with the future work, I should mention that this project is an extension of Ozan Cihangir's PhD research. So this is actually some functioning code, some snips of the functioning code. And what will be done is that using Python, I'm going to be generating the wrapper and the algorithm automatically. So we're going to have the inputs of the bits and the cycles that we want. And the generation test to test everything will be done using scripting and Python. So this will be a more streamlined operation. And these concepts, which I have mentioned earlier, will be even more important in the future. So what is a Wallace tree? I have talked about it for a while now, but well, it's a compression technique for multiplication. So we have a partial product generated tree here, and we compress them. So these boxes actually depict full adders or half adders, and we compress them into 2 lines. Well, these 2 lines depict the final 2 products, which in the unit prime multiplier, and using a final full adder or a standard adder, just we sum them up and we get the final product. So this is a compression method. And a product generator is, well, as you can see, you can actually have all these sub products here depicted in this manner. So we split the inputs, such as these, into 2s and 4s, and we can have them lined up like this, where we can then form them into a Wallace tree. And using custom GPCs, partial product compressors, we can, these boxes depict these, so we can actually have different types of compression, such as this. So for example, here we have a 4 and then 1 here. As you can see, these are fairly standard. These are more advanced. And this is a column compression tree. So what this does is, utilizing these, we compress it into a structure like this. So with this research, there will be Python implementations, and I have shown that the algorithms can be changed to be increased in cycles and the resource sharing and the input widths. So a generator using Python will be implemented, and it will generate the Verilog code. And after that, there will be wrapper generation, testbed generation, and simulation and all implementation all automatically in Python. And afterwards we will move on to the FPGA testing. And FPGA needs to have a certain amount of LUTs, flip-flops, and etc. to carry out these generated operations. So different FPGAs can be used with, so far I have used Basis 2. So yeah, as you can see, we can switch FPGAs. And all right, it's not progressing. And we can actually have application. Well, we can have different designs depending on our application. So these are some of my references. And if you have any questions, I can take them. Oh yeah, thank you.
The next one, the title is Performance Evaluation of Integrated CMOS Photodiodes in 180 nanometer Technology for VLC Systems. And the authors are from Istanbul Bilgi University, Batuhan Yavaşoğlu and Cemre Kut. Could you share your screen, please, and you can start the presentation. Thank you.
Okay, thank you. But I can't share.
No, now you should be.
Okay. Okay, thank you.
Hello, my name is Batuhan Yavuşoğlu. I studied in Bilgi University, Department of Electrical and Electronic Engineering.
Hello, I am Cemre Kut. I studied Istanbul Bilgi University and I graduated at this year in Electrical Electronic Engineering department.
This is our IEEE TUAC project. We are going to present our research name is Performance Evaluation of Integrated CMOS Photodiodes in 180 nanometer technology for visual light communication systems. In this page, you can see our presentation outline. We arrange our presentation in this order. Our problem, in our problem statement, the aim is that designing a system that's called bioelectronics so that it could be used for remote monitoring the statement of health and intervening in situations where it's necessary. In addition, for avoiding the problems that could be encouraged in existing applications such as RF transmitting or non-rechargeable batteries. The purpose of this conference project is to compare the performance of integrated CMOS photodiodes with alternatives available in visible light communication systems. We use 3 different photodiodes and compare them, and then test the performance of the photodiodes through multiple tests. We are trying to determine the most effective components. In this work, we simply maintain the same resistance in dark and light environments on BPW34 and CMOS photodiodes integrated circuits, and obtain different current and voltage values by changing the distance. In our literature search, we did research journals about our chip and datasheet of photodiodes, especially BPW34. We have extract summaries from each article and note that will help us in our project. We search for photodiodes similar to those on the chip. We want to get result from here before starting to use the chip. We decide to test with Arduino and provide the necessary materials. Finally, we integrated the chip into our circuit. We test the efficiency of the photodiodes by making step-by-step measurements with laser and flash in bright and dark environments. In this project, we designed CMOS circuits with a photodiode and reduce light to the photodiode on it and conduct investigations. We monitor it and report the light we drop on the photodiode moment by moment. You can see the general view of IC in this photo. We can program and power it using the photodiode on it. We want to send commands and aim programming by sending laser lights to the photodiode. On light source must be red or ultraviolet due to its wavelengths. For the programming part of the project, we need to send pulses from the Arduino to the chosen photodiodes. We choose the photodiodes BPW34 with wavelength similar sensitivity to the IC. Also, we use some other passive components. We choose laser light source, which is 650 nanometer wavelength, and we use a phone flashlight for easy of use the product. The PCB design part of this project, first we design a symbol of IC with 44 pins and LCC package footprint in Altium Designer. Then we create a schematic for our IC pinout and headers. After preparing the library of the components to be used, the IC is located in the middle of the PCB. Then, for ease of use, double headers were placed on the edges of the PCB from each pin on the IC. Then it was routed from the pins of the IC to the headers with 0.5 millimeter track width.
This is our results page. You can see power photodiode with laser and phone flashlight. We made measurements on the power and triple well photodiode in our IC circuit and a BPW34 with a 5-volt and 650 nanometer laser and phone flashlight. In bright and dark environment, we made these measurements from 0 centimeter to 50 centimeter moment by moment. The x-axis represents distance, the left axis of the y-axis represents voltage, and the right axis represents current. While keeping the laser choose the 1 millimeter in the IC, its value is 500 millivolts. We saw a value of 190 millivolts in a bright room light without laser light. The values in the room light were very variable because we brought an average value. This is because the ambient conditions, the sensitivity of the photodiode and the incident light are constantly changing. For the BPW34, the average value given by keeping the laser close to 1 millimeter is 550 millivolts. The value we see in bright room light without laser light is about 340 millivolts. As we say, these values are approximate because we have constantly taken different values in the multimeter because the light is changing. As additional information, the laser we hold has a wavelength of 650 nanometer and a power of 5 millivolts. In addition, in our measurements with flashlight, some of our measurements varied as the phone flash made a shadow. After some points, we could not see the current. You can see in this graph. This is our conclusion page. Summarize the purpose of this work is to compare the performances of integrated CMOS photodiodes with alternatives available in visible light communication systems. We use two different diodes and three different photodiodes and compare them, and then test the performance of the photodiodes throughout the multiple tests, determine the most effective ingredients. In this work, we simply maintain the same resistance in dark and light environments on BPW34 and CMOS photodiode integrated circuit, and obtain different current and voltage values by changing the distance. As a result, our flash-based results were more effective in terms of availability of flash. So it will be more efficient to use flash instead of laser. Since this project we will develop in biomedical sense and data transfer will be provided by photodiodes for human health, we try to find the most suitable photodiode to detect this data. This is our future works map, taking temperature values using NTC temperature sensors. Then by developing an app, we can send pulses with the phone flash and measure the temperature from our phone. We can measure pressure values using sensors that vary in resistor or capacitance. Also, this is our future works. We take this picture from our lab. Also, programmable digital devices need the clock pulses to operate, so that the programmable biomedical devices operate with clock pulses too. Therefore, we apply clock pulses to IC to get data from IC. Then we will get data from IC and use potentiometer instead of NTC. This is our reference page. We use these references for CMOS technologies, components, datasheets, biomedical research, and integrated circuits. Thank you for attention.
Thank you very much. Could you go back to the slides 8 or 9, please? So, yeah, this could be one of them. So now I am taking my professor hat and try to make some suggestions to all of the undergrad students here. When a person looks at your data or the graph, he or she should understand all of the axes. Like you are writing there 0 to 50, and then in your talk I learned that okay, this was the distance. Then there is 0 to 450, 0 to 1.4. I learned them afterwards. The normal way of doing those things is that writing the labels. So I would suggest to all of you to do that. My question was, how many measurements did you take for all those things? Like, did you take 1, 3? Did you do it in different days and take the average? What was the process?
We did research tests from I think 3 days. We did bright environments and dark environments.
No.
We use foam flashlight and laser light.
For example, the interesting part is that, like, you are telling that you did a bright environment, but bright environment is not a scientific term. I need actually data there, and in different bright days, okay, you may get different results. So my suggestion would be is that when you are doing those measurements, actually like check what was the lighting level and so on. But you did a good job, so I would like to congratulate you and all of the other students.
Thank you.
And
Thank you.
I hope you'll continue with the visible light communication research. Dear all, this is the end of our first day of the TUAC. So I would like to again thank all of the organizers one more time and the students. It is a great opportunity to make presentations, and in the coming years probably we'll do it hopefully live and you will have more interaction, but still this was a really good beginning. I would like to say see you tomorrow for the second day of our